In this exercise, we're going to make the temperature control lab model that we created in the previous activity even more accurate by adding radiative heat transfer. You can see the equation in front of me. This is the energy balance, and we have mass and heat capacity and the differential temperature on the left hand side of the equation. And we have three terms. We have the convective term, the radiative term, and then the generation from our heater. You'll notice that our radiative heat transfer has three constants, and then it depends on temperature, absolute temperature I should note, the fourth power. The circular E stands for emissivity, the sigma symbol is the Stefan-Boltzmann constant, and that A there is the area of the surface that's radiating. We have temperature, ambient temperature to the fourth, and then temperature to the fourth. You'll notice that I said ambient temperature. It's actually temperature of the surroundings, and it's just a small distinction rather than ambient temperature. It's the actual temperature of the surroundings that are receiving that radiation. Before we do that real quick, let's just go ahead and let's discuss some background on distinguishing between convective and radiative heat transfer. You'll notice I have the code hidden with this hide code button. And we're going to go through these quick questions and just kind of discuss I had a teacher who would call it the karma, the intuition behind what's going on, so we can better understand what we're modeling. So for each of these situations, we're going to determine whether radiation, conduction, or convection, or a combination of these best describe heat transfer. So the first one is hair dried with the blow dryer. And you have fluid flow going past that. Even if it's air, it's a fluid. And so that's going to be convection. The heat transfer is happening because of the fluid flow. We'll go ahead and we'll click our box and check our answer, and that's correct. A pan is heated on a gas stove. We don't have too much soot, which is what causes radiative heat transfer. So again, it's that fluid flow, even if it's a fluid on fire. It's that gas stove fluid flow that causes that heat transfer. So that one's going to be convection as well. Next we have food cooked on a pan. That food is sitting on that pan and there's solid contact between those. And so that's going to be conduction. That solid contact is what denotes conduction. Sunlight warming the ground. As we think of the little particles that are emitted for radiation, photons and light is what we normally think of. So that's a textbook example of radiation. Next we're going to discuss as temperature increases from a low temperature to a relatively high temperature, which heat transfer mode increases relatively more. So we have convection and radiation. We'll actually look at the equations down at the bottom of our screen. We have both convection and radiation there, and you'll notice that radiation depends on the difference in temperatures to the fourth power, whereas convection is just the straight up difference. So radiation will be impacted even more by that change in temperature, especially as we get higher. T to the fourth is changing much at a higher pace than the temperature. So radiation is going to be changing at a higher pace. Finally, we're going to discuss which factors affect only thermal radiation and which ones affect both thermal radiation and convection. So we have heat capacity, and we don't note heat capacity in either one of these equations. Heat capacity has to do with the energy balance up here, but it doesn't have to do with radiative or convective heat transfer explicitly. The same could be said about mass, and so really the question is between emissivity and surface area. We'll note that surface area is in both of these equations. So we'll go ahead and we can answer 2 first. And then finally, which of these factors only affects thermal radiation? Well, that's going to be the last one, emissivity. So we're going to move on to our problem statement. We're going to do something similar to what we've done the previous times. We're going to use this lumped parameter model, which includes both convection and radiation all in one model. We have our constants here for mass and emissivity, surface area, heat capacity, our convective heat transfer coefficient, and our sigma, as well as the ambient or temperature of the surroundings. I'm going to go ahead and we're going to show how much heat is lost due to convective and radiative heat loss throughout a 5-minute period. I'm going to go ahead and show the code now, and we'll go down to our code. The first thing I do is I want to, if we look at the left here, I want to output the results in a CSV file, so that in case I make an error later on, I want to be able to have that saved, so that if there's an error I can just load that rather than running the TCLab again for 5 minutes. So what I'm going to do that is I'm going to create this variable called temp, and this I'm using MATLAB 2021A. And so when I use this argument, matlab.desktop.editor get active, it returns the path to this specific file. And then I return the directory, and then our absolute path argument right here is the path to the directory or the file folder name, so L4, and then the file name that I've specified here, L4 TCLab data. I'm also going to initialize number of seconds and the time arrays right here. Next, we're going to first try to read the file and separate it out into time and temperature, but you'll notice that file's not there, we can already see. So we'll move on to the catch portion of this code. We're first going to connect to our temperature control lab. Next, we're going to loop through. We're going to have our initialized storage arrays for the final results with T1 and time, or TM I use it for time, that way we don't get it confused with time up here. Then for 1 to n plus 1, so for 301 seconds, or 301 time points I should say, we're going to save the time using this tick and then talk, so record the time measurement. And then we're going to record the temperature using lab.t1. And then we're going to plot it just so we can see how it progresses. This is from a previous trial. We'll go ahead and we'll start that again. First though, let's discuss how we'll be using, actually let's do that first. We'll go ahead and run it and we'll look at our results. I'll go ahead and I'll speed this up now. We'll look at this in an accelerated pace. Alright, here we have our final graph. We can see that it increases pretty steeply and then tapers off at just under 50 degrees. Let's go ahead and now let's discuss how we can use this energy balance to solve for each term. So we're going to use ODE 45 to simulate through. I want to simulate this TCLab temperature. Then we're going to say what the total TSim, the convection portion is the difference between ambient and TSim, times U times A, and we have the radiative term. You'll notice with the radiative term, we have the dot before the to the fourth power, and so that's what that's doing is instead of multiplying 4 arrays of TAK, we're taking each element of TAK and raising it to the fourth power. So that's what that dot symbol does, is each element it applies this operation to each element of this array. So we're going to go ahead and we're going to look at the lab sim real quick just to go over that function. Here we don't have temperature explicitly dependent, So I have it tilde there. We have our constants, UA, alpha, epsilon, sigma, TA, Cp for heat capacity, M, TA, K is ambient temperature in Kelvin, TK is the temperature of the temperature control lab in Kelvin, and dt is our differential temperature. We first have our convective term, pretty straightforward, we've done that a number of times. We have our convective term, which includes both ambient temperature to the fourth minus the temperature of the control lab to the fourth, plus alpha times 50, which is the alpha is the conversion between heater percentage, which is 50 here, and the actual Q, wattage output, and all that divided by M times Cp. And that comes straight from our energy balance that we've done before. Let's go ahead and let's look at the graphs that result from this now. We have our graphs, just two subplots, 211 and 212. The first one's going to hold the time with respect to the temperature and the simulated temperature. And we're going to graph our convection, radiation, the energy lost, and then the gain. So we'll go ahead here. We'll run this section and look at the results. So you can see our temperature is lower than expected, and that's been a pretty solid pattern. That pattern could be due to a number of things, but the main thing is the more in depth our model is, the more and more ability to lose heat our temperature control lab has. If we look at the energy, we're looking at how different ways that we lose energy here. We have convection and radiation, and they're going pretty similar, but as we go further and further, radiation becomes a larger and larger portion. And then you can see that this yellow line is how much energy is lost. The sum of convection and radiation is equal to gain, and so we don't see that line, which is a good thing. Otherwise there would be something off and we'd want to know. So that does it for this temperature control lab activity.